Hello everyone, welcome to this video on field theory. In this video we shall see that every finite extension that is also an algebraic extension. So there's a theorem which says the same thing. They're saying if E is an finite extension of F, then E is also an algebraic extension of F. Now this is a really useful result, and we can take this to be a definition for an algebraic extension. Whenever you see an finite extension, that means the degree of that extension over F, that is given to be a finite number n, then we say that the given extension is algebraic extension. So let us look at the proof. The proof is also really simple. To prove an extension E to be an algebraic extension, what we do, we consider an element in this, and for this element we will try to find some polynomial in this field F, say Px or Fx or whatever, such that P of u is equal to 0. If this is true, then u is said to be algebraic element, and so we have shown this one element to be an algebraic element. In that case, if every element of that particular extension is algebraic, then we say that the extension, this is an algebraic extension. So here we are given E is finite extension, that means its degree over F, that is a finite number, let us call it n, and let us assume u to be an arbitrary element from this extension. Then according to this result that we have seen in the earlier video, this set, if the polynomial is of degree n, then the set 1 u up to un minus 1, that is a basis set for the extension, right? Now because the degree of this polynomial E over F is n, that means we go up to n minus 1. So 1 u up to un minus 1, that is a basis set for this extension field. Now if you add, what do you mean by a basis set? That means that this contains linearly independent vectors which are sufficient to generate whole of this extension field. So now if I add one more element, say u to the power n, to the set of n linearly independent vectors, this set now becomes linearly dependent. So by definition of linear dependence, we know there exist scalars a0 up to an which are not all 0 in F, such that the linear combination of these together with the set is equal to 0. So this is by virtue of the definition for linear dependence. Now can you see from here, we have found one polynomial such that u is a root for that polynomial. Let us call this polynomial to be fx. So and which is equal to a0 plus a1 x plus up to an x raised to power n, that is the polynomial. Now if you calculate f of u, that simply comes out to be a0 plus a1 u plus up to an x u raised to power n, and that is equal to 0. That means for this polynomial in fx, we have an element u in E such that f of u is equal to 0. Thus u is an algebraic element over F. U belongs to E, that is an algebraic element over F. Now remember, we considered this element u to be an arbitrary element. Therefore every element for this extension, that is an algebraic element over the given field F. Thus we can say that this extension is an algebraic extension of F. So the proof was quite simple. So every finite extension, it implies algebraic extension. Let us see one consequence of this theorem. So remember this theorem where for any px irreducible polynomial, if u be the root, then this set was the extension field, and if the degree of that polynomial was n, this set forms the basis, and the degree of that extension field over the given field was n. So using this theorem, we can state that if px is some minimal polynomial of u over f, that means px is the monic irreducible polynomial such that u is a root of that polynomial over f. In that case, and the degree of that polynomial is n, in that case we can say that the degree of the extension field f of u over f is equal to n. So that means if we have the degree as a finite number, that means we can say that the extension f of u over f, that is a finite extension. Moreover, we just saw that every finite extension is an algebraic extension. Therefore, the extension created in this sense, f of u, that is also an algebraic extension. So let us see what we have done over here. It says if E is some extension of f and u is some algebraic element over f, then f of u is also an algebraic extension of the given field f. So this is the result. So you see, f of u is the extension, f of u, that is the extension field for f, and moreover this E, that is an extension field of f of u. So this is also a useful result which we shall use further. So well, that is it for this video. I shall see you in the next one.